Now we are going to study what is motional EMF. We know that whenever there is change in magnetic flux, EMF is induced in the coil. The EMF induced across the ends of the conductor due to its motion in the magnetic field is called motional EMF. So motional EMF can be derived like this. We can assume a rectangular loop PQRS. This is PQRS in which the side PQ is movable. Side PQ is free to move and this is placed in a uniform magnetic field. So this cross represents magnetic field into the plane of the paper. Okay. Now the rod PQ moves towards left with a velocity v. When this rod PQ moves with velocity v, what happens to magnetic flux? Magnetic flux varies. Magnetic flux decreases. Whenever there is change in magnetic flux, we know that EMF is induced and hence current flows through the loop. And that current is called, and that EMF is called motional EMF. The magnetic flux enclosed by the loop, here this is the loop. What is the magnetic flux enclosed by the loop? Here length is L and breadth is X. So magnetic flux is given by, we know it is B dot S. Okay, magnetic flux is B dot S is equal to B. S represents the area, here length into breadth, here Lx, and here Bs means actually it is Bs cos theta. Okay, area means length into x, L into x, theta. What is theta? Theta is the angle between magnetic field and area vector. Magnetic field is into the plane of the paper and area vector is also in the same direction and hence theta is equal to 0. So magnetic flux enclosed by the loop can be written as phi b equal to Blx. Okay. So when the side PQ is moving with velocity v, what happens to magnetic flux? Magnetic flux varies and hence EMF is induced. So the induced EMF can be written as induced EMF E equal to, we know it is equal to minus d phi b divided by dt. This magnetic flux varies and hence EMF is induced. This induced EMF is, we know it is E equal to minus d phi b by dt. That is according to Lenz's law. So EMF E equal to minus d by dt of, what is this magnetic flux phi b? Blx. Blx. B and L are constant. So Bl minus Bl into dx divided by dt. And here dx by dt, rate of change of displacement or rate of change of distance, it is actually minus v. Why? Because as time increases, when this conductor is moving towards left means as time increases, what happens to x? X decreases and hence v is negative. Time increases, x decreases. Therefore v is negative and hence we can write minus Bl into the velocity minus v. So EMF is given by Blv. And this EMF is called motional EMF. E equal Blv is called motional EMF. This is called motional EMF. So the formula for motional EMF is E equal to Blv. Now let R be the resistance of the loop. Loop having resistance R. Now the induced current can be written as, let R be the resistance. R be the resistance of the loop or resistance of the conductor, and hence induced current can be written as, induced current is equal to, we know that induced current is EMF divided by resistance. So it is Blv divided by R. Now what is the direction of this induced current? Direction of induced current is given by Fleming's right hand rule. Okay, so Fleming's right hand rule that gives the direction of induced current. Fleming's right hand rule states that stretch the forefinger, middle finger and thumb of your right hand mutually perpendicular to each other, so that forefinger represents the direction of magnetic field, thumb represents the direction of motion or force, then middle finger represents the direction of current. Here what is the direction of current through the side PQ? Here magnetic field is into. Okay, cross, no, magnetic field is into. The side PQ is moving towards left. So what is the direction of current through the side PQ? Current is in which direction? Downward direction. So through the conductor PQ, current is in the downward direction. So what is the direction of induced current? Direction of induced current is P, Q, R and S. Okay. Rule is, if we stretch the thumb, forefinger and middle finger of our right hand mutually perpendicular to each other, and if the forefinger points in the direction of magnetic field, thumb is in the direction of motion of the conductor, then the middle finger points in the direction of current. Using this rule, we can find out the direction of current here. What is the direction of current? Here, magnetic field is into the plane of the paper. Then thumb is towards left. So what is the direction of current? The direction of current through the conductor PQ is in the downward direction. So this is the direction of current. So using Fleming's right hand rule, we can say that the direction of current is through the loop, it is P, Q, R, S. Now we know that this is a PQ is a current carrying conductor. Okay, PQ is a current carrying conductor carrying current I, length L, same length L, placed in a magnetic field B. So PQ is a current carrying conductor of length L, carrying current I is placed in an external magnetic field B. So what happens to the conductor? It experiences a force. So force experienced by the current carrying conductor is given by F equal to BIL sin theta. Okay, the force is given by F equal to BIL sin theta. And what is the direction of this force, and what is the angle theta here? Theta means angle between magnetic field and length in the direction of current. Magnetic field is into the plane and length in the direction of current means downward. So both are perpendicular to each other. Therefore theta is equal to 90 degree and hence the force experienced is BIL. So force experienced by the conductor carrying current I placed in an external magnetic field is F equal to BIL. And the direction of force, we know it is given by Fleming's left hand rule. Okay, so using Fleming's left hand rule, what is the direction of magnetic field? Into the plane. What is the direction of current through the conductor PQ? Downward. So magnetic field is into, current is in the downward direction. So what will be the direction of force? The direction of force is towards left. So this is the direction of the force experienced by the conductor. So direction of this force is given by Fleming's left hand rule and it is towards right. So we know F equal to BIL and we have derived current as, what is the value of current? Current is given by BLV divided by R, isn't it? Length L. So the force is given by B square L square V divided by R. So the force experienced by the conductor is given by F equal to B square L square V divided by R. Thus this force due to induced current acts in the outward direction, that means towards right, which is opposite to the velocity of the arm. We know that velocity of our arm is towards left and the direction of the force is towards right. Hence, to move the arm with a constant velocity V, it should be pulled with a constant force. Okay. Now, what is the power supplied by the external force? Power delivered by the external force is P equal to, what is the relation between power and force? We know that power equal to force into velocity. Fv is power, F dot V, that is actual formula. Power equal to F into V. Force, what is the direction of force? That what is the value of force? B square L square V divided by R into V. So it is power supplied by the external force is given by B square L square V square divided by R. And also power dissipated as joules heat is also B square L square V square divided by R. Hence we can say that the mechanical energy expended to maintain the motion of the movable arm is first converted to electrical energy and then it is converted to thermal energy, and hence it is completely inconsistent with the law of conservation of energy. Rectangular loop PQMN with movable arm PQ of length 20 cm and resistance 5 ohm is placed in a uniform magnetic field of 0.2 Tesla acting perpendicular to the plane of the loop is shown. Calculate the EMF induced in the arm PQ, current induced in the loop when arm PQ is moved with velocity 15 meter per second. Figure is given. So we know that EMF is given by, what is the formula for EMF? EMF is given by BLV, because it is placed in a magnetic field. This loop is placed in a magnetic field. Here the side PQ is moving with a velocity. So EMF is given by, what is the formula for motional EMF? We have the motional EMF E equal to BLV. Clear? Now we can substitute, all the values are given. Magnetic field is given by 0.2 Tesla. Length, what is the length given? 20 centimeter. 20 into 10 raised to minus 2. Velocity, what is the velocity given here? It is moving with velocity 15. So into 15. And it is equal to, what is the answer? 0.6 volt. Clear? Now what is the current induced in the loop? We have the current, induced current is given by I equal to EMF divided by resistance, is equal to, what is the EMF? 0.6 volt divided by resistance of the loop is, in the question it is given as 5 ohm. Okay, 5 ohm. So after simplification, current is given by 0.12 ampere. Okay children. Two identical loops, one of copper and other of aluminium, are rotated with same speed in the same magnetic field, in which case induced EMF, induced current will be more, and why? So one of copper and another of aluminium, isn't it? They are moving with same speed in the same magnetic field. So we have motional EMF equal to BLV. So magnetic field remains same, identical loops. So length may be same, moving with same speed. So velocity will be same. So since all the values are same, what is the induced current, induced EMF? Induced EMF will be same in both the loops, because it does not depends on the nature of the material. It depends only on magnetic field, it depends on the length, and depends on the velocity. So induced EMF is given by BLV, and all the values are same for aluminium loop as well as copper, and hence induced EMF will be the same. Now what about the induced current? We have induced current is equal to EMF divided by resistance. So induced current depends on resistance. So which one having lesser resistance or higher resistance? Resistance of copper is less than resistance of aluminium. Resistance of copper is less, and hence since resistance decreases, what happens to current? Current increases. So resistance of copper is less, and hence induced current in copper is more than that of aluminium. Okay, so induced current will be more in copper loop, because resistance of copper is less than resistance of aluminium.